So while I get everything set up, this is SOC 105 series from Level Effect. We're doing reverse engineering, light reverse engineering from the perspective of malware analysis. And we've already gone through PowerShell deobfuscation, full infection chain with like .NET binaries, process injection, donut shellcode, even extracting configuration from a remote access Trojan. Hey, Morphine. How's it going? And yeah, so, or remote access tool, I should say. But now we're actually going to be diving into a little bit more. So just getting screen shared here. Good morning. How's your day been so far, Karina? I'm glad to see you here. All right. Nice. So let's jump into that. So I'm going to start the range here. Okay, that'll be a few minutes. So I'm thinking today, I was thinking about where we are now with what we've covered, and what I was hoping to cover with more low level things, decompilation, and even maybe a little bit of assembly. But that might be a bit too much of a jump because we just got done with PowerShell and analyzing .NET binaries through dnspy, which is generally easier on analysis than, say, analyzing decompiled C or C++ code. So we are going to be taking a look at that. We are still going to be using Ghidra and even x64 debugger, but maybe not so much into the realm of assembly. That might have to come later. But I have prepared something that hopefully is a little exciting, and it's something that when I encounter malware, it's very often seen. All right. So if you want to follow along, this is the reversing lab systems in the SOC 105 course object. And we're just going to be using Windows today. So if you want to save on credits, you can just stop your Linux workstation. All right. So this will again just be hands-on. I'm going to be going through one or two labs and answering questions. I'll even talk about some concepts like compilation and decompilation, and I'll show that off here. Yeah, the red Windows logo. Yeah, I don't remember where I got that. Definitely not Microsoft sourced, that's for sure. But I'm sure it'll come up just with a quick query online. I do remember it was hard to find a really high resolution for it though. All right, so we're going to be dealing with RIC.exe and mangled packed.exe today. For RIC, I want to actually show, we'll start VS Code here. I want to show compilation rather than just talk about it. So, and I actually should open the other Visual Studio. It's going to be easier to compile this since it's in C or C++ rather. So it's going to take a bit to load up on these boxes. This one was just reset, so if you're on these VMs as well and they're a little bit slow initially, that's normal. After some time, they kind of warm up. All right, so we actually don't want to use this, so I'm going to close that and open up Visual Studio 2022. Okay. All right, so this is the first time I'm opening Visual Studio on this box. What I want to do is let us actually, I should just create a new project. And yeah, new project. And we're going to be doing C/C++ here. I think that this is C. C++. So we're starting off. I have some source code written in C++, just a small routine. I want to show what it's actually like to compile a low-level language. And when I say compile, for those unfamiliar with compilation, programmers, well, we've already gone over programming languages, right? There's source code that is readable to us as developers, as programmers, and certain languages that they're called compiled languages, and usually faster and more low level. The process of turning those languages into programs that you can actually run, compilation is part of that process. And compilation brings the source code, that form, down to machine code that can be interpreted by the operating system, particularly the processor. So that's what I want to show here. And I could get into a lot of the theory, but I think it's better just to get this set up. So what we're looking for is and I can actually just go by language here. Yeah, Visual Studio 2022 is pretty chunky, so as you can see, it's taking a while to start up. And while that's doing that, I will just handle something on the side here. Okay. So we want C++, and we'll just do a console app. So there's a difference between console app and a GUI app. Console as if you're running it from the command line. And in that way, you can even hide the console in that case. You don't show a window for a user to interact with. A GUI is graphical user interface, and that's the other type of application that you can make. So we'll just call this Rick. And all right, that looks fine. We'll put it there. Oh, I haven't been looking at the chat. All right. Oh, nice, Doug. I see you're on. Good to have you, man. All right, so when we start out, it's just boilerplate stuff. Wow, that's pretty darn slow. But I have here a program. So this is rick.cpp. We're going to replace this. And so the way this works is the source code is in files like .cpp, in this case C++. There's also C, which is similar to C++, but they have their difference in that C++ is more of an object-oriented language, which is something that we talked about in the past streams. So to compile this, and I'll go over what this code is in a second here. We can use the Visual Studio compiler. And so this is the source code. And we run a build, in this case, in a debug version. And all right, that's taken a bit. That's taking a lot of it. Okay. Had me worried there that just a simple build was going to fail. All right, so we're going here. This is the perspective, for those unfamiliar, of coding and building C and C++ programs. When I do implant development, it does not look very different from what I'm doing now. Maybe except for tinkering a lot more with settings and getting at least some scripts in here to make this a lot less of a manual process. But yeah, this is pretty much it, going from source to compiled, which we can see here under the output folder. It's compiled for x64, so 64-bit is modern Windows, and rick.exe. So if we run this in its console application, all right, so we get a YouTube URL. So what's going on here? And I'm actually curious, who in the chat is familiar, at least to some extent, with C or C++? So far, what have we covered? Python, C#, PowerShell, and I think this is the first time we're actually handling a compiled language. Okay, a bit familiar. So this is commented. That's what these lines are with the leading slashes. This is just documentation to explain the code. And it's only a little bit of code, but it's actually something that in malware analysis you would encounter quite often. And this is called an XOR operation. XOR is a type of encryption, or you can even call it encoding. And pretty much it turns plain text readable to us into encrypted ciphertext. And in this case, actually, it's decrypting ciphertext that's already stored in the program like this in bytes represented as hexadecimal, and stepping through this, the main function. So in C and C++, usually the entry point to a program would be the main function written by the developer. There often is a lot more of like preliminary setup. There's actually a real entry point when it comes to the C libraries that even comes before this. But for what matters to us right now, you can consider main to be the entry point to a program. And this is very particular to C++. It sets up a namespace, which is just the unique area of the program where this code resides, and it has a certain name of standard in this case. So when main is executed, in the chat, high school student, dream is to become a cybersecurity engineer or analyst. Like the videos. Awesome. I'm really glad to hear that. Yeah. Do you have any interest in malware analysis, reverse engineering? Cybersecurity is a massive field, so I always follow through when I see someone's interested in the field, what they have interest in, and yeah, but that's great to hear. So main is invoked, and what's going on here? Remember we talked about variables. A key variable is set with this never going to give you up, and some people might have already understood what the end game here is for this particular program. And here's where we actually define an array of the encrypted bytes. And it's like this in many languages, but at least in C++, when you see this is the variable of that array, and then it's denoted with these square brackets, that's the actual indication that this is an array. And very different from Python, you'll also notice that there's explicit typing here. So C is C++ is a strongly typed language where you are required to actually, when you initialize a variable or when you set a variable, to explain what type of variable that is. In that case, this is just a simple string, hence that's a type string. You can even initialize empty strings, and that would still be type string. The white theme is hurting. Okay. Let's see. I don't think I've ever actually set dark mode, but I definitely, let's see here. I sympathize. What would that be? I guess edit preferences or something. I'll look this up real quick. Oh, there you go. Oh, no, that's good. Wrong place. Let me look that up. Visual. Yeah, I think it's worth taking. I know Anthony's going to fight this, but I'll take a minute or two just to get dark mode on this thing. So just sit tight. Visual Studio 2022 set dark mode. Tools options. Do not expect that to be the place for that. All right. Environment. Keeps the eyes strong. There we go. That doesn't look bad. This is the first time I've actually using Visual Studio with dark mode. All right. And actually, it makes it easier to read in a way, and reminds me, for the purpose of the recording, I'm just going to make that a little bigger. So where were we? The way that XOR operations, you'll usually see decoding or encoding in the form of a for loop. And just a reminder, a for loop is, say you have a list of items, a list of strings, integers, whatever type, and you iterate through that list, meaning you are processing each item in that list sequentially. And that's exactly what's going on here, where you're starting at index 0, meaning the start of the list, and in this case, the list is that's being processed is within the for loop, That's denoted by the squiggly bracket. So the actual what's happening with the action being taken is this portion here. And so this is saying starting at 0 up until the length of the array. I keep on saying list because I'm coming from Python, but I should say array. The array of bytes. So pretty much for the entirety of the length of the byte array, do this thing, and every time that it processes one item, increment the counter for where we are in the loop, the iterator. So what that means is that it's going through every byte in this array and XOR decoding it. And that's what this operation is. When you see a caret sign, I think this goes for most languages, in fact, that is XOR decoding or XOR encoding or decoding. And that's happening against this key. And so the interesting thing here is that the key is not the same length as the byte array. And if this were, it would be a very different output if it were just the key XORed to this byte array, just directly one-to-one. But what's actually happening here in this portion, it's actually cycling through the key. And that's what this modulus operation is enabling. Mod is division with a remainder. And that remainder that comes from running the iterator mod the length of the key means that starting at 0, there or if it's even, I guess. Either way, it would eventually have remainders that keep on building. Say remainder 1, so it cycles through 1 there. Remainder 2 cycles through 2 here. And so you can see that it would actually cycle through the entire key while it's iterating through this loop. So therefore, it uses up the whole key for whatever length of the loop happens. Hopefully, I explained that well. I probably didn't, but anyone who wants clarification on that, by all means, ask away in the chat. But yeah, maybe I should just summarize that. XOR is ciphertext, and it's against a provided key. And usually when you see it, it's going to be a for loop that applies that key to the ciphertext, and out comes the plain text. And that's what's actually happening here. The plain text string, this plus equals, is appending the output of this ciphertext decode to that plain text in its unencrypted form. What is the length of the key loop happens? The length of the key loop is calculated here. And this is using built-in functions to make that happen. So pretty much what's going on here is that CT length holds the length of this byte array. Yeah. And it's just real simple from there. The result that's printed out is the string of the, it's pretty much the plain text that was built from that for loop. And that's exactly what we're seeing when we run this. Where did the thing go? Doesn't matter. I guess we'll just, oh, it's PowerShell, that's right. It's exactly what happens when we run this. So this becomes that. And that's going to look quite different. You'll see we're going to work with decompilation, and this is going to get turned on its head. So that's what we're going to switch to right now. But I wanted to give a little bit of a background again on what this looks like in the source code and how that translates to actually becoming an executable. And also just going to pop that link in there for anyone who is curious what that is. All right. Now for the fun stuff, at least for me. We're going to actually tackle a big part of malware analysis. It's something that you're going to encounter time and time again, and that's packers encryptors. High level, they have a lot of similarities, but I would describe a packer as a form of compression, and depending on what is used, it could also be encryption involved. So it's some combination. It's not necessarily or. It could be a combination of compression and encryption and even virtualization, where the code that's run in a program is not getting too deep into it, but its runtime is virtualized, which actually makes it more difficult to analyze. So the packer also, because it provides compression, it will rather effectively reduce the size of the binary as well. And then encryptor is very much like a packer, but it's focused on encryption. It's not necessarily about making the binary as small as it can be. So you'll see malware very often either packed or compressed, no matter the attack, the stage in the infection chain. Even if it was injected into a process and it's in memory, it can still be packed. It can still be encrypted. So what we're dealing with here is mangled packed.exe. And while I talk about this, I'm just going to get some of the applications we'll need ready here, seeing as everything is going at about 2 miles an hour on this VM right now. But these are pretty heavy programs in its defense. So we're going to start a debugger, and I'll talk about what that is. And we are also going to might as well get Ghidra going. Where is that? Ghidra, there you go. So this is an interesting case of packing. This is by UPX, which is probably one of the most well-known packers out there. It's open source. You can get to it on GitHub. And there was a time when it was very, very often used by malware. I would say that it is not as often used. You will still see malware packed by UPX, but there are many, many other options out there, and it's just now one of a sea of many other packers. But it's still a classic, a good one to start with when actually encountering these sorts of things for the first time. So before we go into Ghidra or a debugger, let's do some static analysis and see what we have. So we've used before detected easy. That's excellent for just getting information on the file type, some heuristic scanning, information on entropy. We talked a lot about entropy in the last, I think even in both of the last two streams. So let's pop this in here. And this is where entropy is actually matters a lot more. Okay. All right. So as always, detected easy is awesome. Detects that this is a UPX packed executable, 64-bit, and it's using version 3.96 of UPX, which does matter. The behaviors of packers can change between versions, and it can you would sometimes have to adjust with your analysis depending on the version you're dealing with. So this is a heuristic scan as well, that it's seeing compressed or packed data. We can even actually go directly to the not there. If you click on this S, I believe, yeah, you can actually see. Let's see here in detected easy. If you're curious about how these heuristics are run, you can actually view them directly by going to that window, and there's a lot here. So if you're curious about binary analysis and how antivirus companies detect these are the sorts of things, these detections that they make. and that contributes to the heuristics, this result here. Question, is it possible for malware to have layers of payload that execute as it unravels? Yes. So I guess there are multiple levels to that. If we talk about layers of execution, malware infection chains can have multiple stages. So say you have an initial access through a user clicking on like a shortcut file, or /LNK, you can call it. And that LNK invokes some script that downloads an additional, let's just say a batch script. And that batch script then pulls from a staging server another payload, which is say a DLL. And then that DLL is proxy executed to drop, maybe it was stored inside of it, an entirely other executable. And then that executable is a loader for maybe it injects into another process, a running process. And that code that it injects, shell code, is like command and control that has a reverse shell out to the attacker infrastructure and gives the attacker remote command capability on that host. So that's on the more macro level. If we're talking actual execution of the malware, and if, what's the question again? Layers of payload that execute as it unravels. Yes. We will actually see that right now with packing. That is a great way to describe how these things are unpacked. And we'll be stepping through that in memory as it executes. So other question, were the layers something we saw in RE3 with PowerShell, base64 encoded, decoding? Yes, exactly. RE3 is a great example, the last stream that is, of unmasking each layer of the malware. That one was quite a bit. It was like PowerShell and then .NET reflective assembly load in memory, which then had like donut shellcode that was, if I recall, injected into some Windows binary. And that turned out to be what was injected was quasar rat. And then we fetched the config from that rat. So detected easy is spot on. The other thing that's really great about it, if we just click on advanced in the right here, we get more options. I really would like to see entropy, because entropy, we talked about it before, but it matters a lot more now. This is a big part of determining if an executable or parts of an executable are packed. And this entropy is, say, around 7.5. That's quite high. That's actually very, very high, 7 to 7.5. And at least in these sections, the header and this initial section that, and you can even see it as plain strings, UPX is in there. So speaking about that plain strings, let's spin up a hex editor so I can actually show how UPX has changed what this executable looks like. So let's put that into HXD. And we still see the MZ bytes because this packed executable still needs to run. It still needs to work with Windows, which is expecting it to, well, be a portable executable format, have an MZ header. There's that DOS stub that everyone knows about. But then, and you won't always have this depending on if there's been any like tampering with this packer or the result of the packing. You can sometimes see strings directly in the packed executable that give away what packed it. Not something that you'll see all the time. And in fact, this one here should even say UPX, but that was mangled. That was bytes replaced, because this is how easy it is to replace bytes. Say if I want to bring that back to what it was, that would be 55 for, oh, let's see, process cannot access because it's used by another process. Probably because I have it open in dnspy. Let me close that. dnspy already probably had a handle to the process, sorry, to the to this binary that I have here, and nothing else should have a handle to it, I believe. And this doesn't even have it loaded, and Ghidra is not loaded. Okay, so I should be able to mess with this now. Let's see. Yeah, there you go. All right, so I mean, this, it looks simple to those who've already seen this, but this can really blow people's minds. that you can, even after compilation, after we turned our source code, our program, into an executable, you can still modify it, and malware developers very much make use of that. They will swap out bytes. They will um, do it in such a way that it won't break the program, because there are key, like, critical sections in this executable where you can't really just tamper with it without causing corruption. But in other ways, say MZ is very often used as an indicator that this is an executable. Malware will actually wipe that out to throw off detection. Say if there's like memory scanning and this thing's running in memory, it will replace that MZ header by something else entirely. Maybe it even like nulls it out with null bytes there, just zeros. So if the security solution is just looking for that MZ header, they're not going to find it. So they're going to miss the malware if they don't have like a layered detection for malware behavior and heuristics. So going back to what that was, originally this was 414141, which is A. What that means is that this particular packed executable was mangled. And mangled means that it makes it harder to unpack it, because just you can use the UPX tool to pack it. All the same, you can use the same tool to unpack it. So threat actors don't like that. That's too easy to do that. So they would mangle the output executable to make it either very difficult or near impossible for the tool to be able to bring it back to its unpacked form. In this case, it's a very simple mangling, so we can easily reverse this. But that's fine. I'm just going to go ahead and not save that. So before we jump into Ghidra and Debugger, let's just run this. And I believe it's a console application, and we'll see what this does. So this is called Mangled Packed. All right. So it wants a password, and let's just say, let me in. Incorrect. All right. So I can already say now that password's not going to be guessed. So it's already providing some sort of an obstacle, and this is where reverse engineering comes in. This is where even after the program has been compiled and it's an executable, we can peer into it given specialized tools and look into its internals and see if we can bypass this password check. That's the first thing that comes to mind. And you might be thinking, how does this relate to malware? Well, malware, at least these days, more often than not, the time spent reverse engineering is not necessarily understanding the malware's capabilities, like its actual functions. It's just getting to the decompiled form of that malware, because it does things like anti-analysis. It checks if it's running in a sandbox or VM environment. If it does, maybe it exits, maybe it just acts like it's doing something else benign. So a large part of reverse engineering is just getting through all these obstacles in the malware, whether it's packers, cryptors, anti-analysis, evasion, anti-debuggers even. All that stuff you have to get through before you're even able to look at some code or some assembly. That's very, very common. And yes, obfuscation is a big part of that as well. And obfuscation is put simply, it's just hiding data that can give away the functionality or capabilities of malware in such a way that makes it hard to read. Not necessarily encryption. I would say that's a different thing. It's more often used with like encoding, whether you're using base64 or hex encoding, or even like you encode it into decimal format. That's considered obfuscation. So, all right. Let's actually, now that we know that this thing is putting up a fight, let's take a look at it in Ghidra. So with Ghidra, you first have to create a project, and you can just make this non-shared. And we'll just call this packed. And you can just drag and drop. Question. I guess that the obfuscation we saw in RE3 was pretty easy to detect versus what Cyberkata was saying about it going undetected. Fairly, I guess. Like there was a lot of base64 usage, but that's the thing that there is also a lot of legitimate activity from system administrators, for example, that they use base64 encoded commands when they run their PowerShell scripts, and even things like WinRM are going to use base64 encoded PowerShell commands by default as well. Oh, and then also that other thing like replacing garbage strings. Yeah, that is actually very effective. It's simple, but it is effective. Yeah, that's a good one to point out from last stream. So okay, in this case, Ghidra does a pretty good job of understanding what type of executable we're feeding to it. So we don't really have to do much in telling it how to analyze. So we can go ahead and just double click that, open Ghidra. And so while this is opening, and it's actually going to go through analysis as it decompiles, disassembles and decompiles, I'll go over the tools that we're about to use here. So we're going to say yes because we want to analyze this program. And I don't think there's any need to touch any of those. It should work just fine without going that far. So to describe the tools that we're about to use for this, Ghidra is good for disassembly and decompilation. So first I'll talk about decompilation because we just talked about compilation. So with compilation, we went from source code compiled to machine code, which became the executable. Now we're going backwards. We have the executable that we want to now bring back to source code, or at least the closest that it can get to source code. It will never be the original source code because there was a lot of manipulation that happened in the compilation process, that the executable kind of lost the state of what that source code was. So things like function names, variable names, certain intricacies of the source, those won't necessarily be clear from the decompilation output. So to summarize, what we were doing before was making a program, compiling it to an executable. What we're doing now with Ghidra is taking the executable and decompiling it back to as close to the source code as it can get. Kind of, I really shouldn't call it guessing the source code, but to make it simpler, it's like a best guess of what the source code was, even though it's not like a probabilistic thing. It's very much definitive. Are these manipulations the compiler optimizations that you need? Yes, that's one part of it. Compilers do optimize, and in order to make the program execution faster, they will move around what happens during execution and control flow. So it can look very different from the source code, yes. All right. And the other tool that we'll be using is x64 debug, this little bug thing down here, which is now open that. And kind of cool is that when it's running, it uses the red eyes icon. And what this is, it's a debugger, and this allows us to actually execute the program, but be able to pause it during certain times. So we can analyze it and most importantly, view its memory, because remember, when a program executes, it loads its runtime is in memory in a process, right, on Windows. So and that's really useful in case, for example, say when it's just on static on the file system, it has a lot of encrypted strings. It doesn't decrypt those strings until it's actually launched and in runtime. So if you have a debugger and the program is running and it's already decrypted the strings and it's now in memory, you can view those decrypted strings. And for example, in real world, large organizations, you'll see Defender and Bloodhound doing a lot of activity that emulates an attacker. Yeah. Having pen testers, red teamers, like internal teams, that can confuse as well. and look like intrusions, but it's all about communication to make sure that if there is like an in-house SOC or managed detection and response, that they know that that's sort of expected activity, unless they are the ones who are actually being tested by the red team, which is quite likely. So, okay, question, just so I understand, is it the compiler optimizations that make it hard to get back to everything, like the source code when decompiling? That's one part of it. Yeah. A very large part of it. Yeah, it's the way that the compiler works, and the optimizations make it harder, I would say. So we'll get into the debugger in a bit, but first, I want to perform some static analysis on this packed binary. So we can see some of the sections here, and there's that mangled section over there as well. So we're currently at the entry point. Ghidra will bring us to the pretty much the first point of execution in this code. So here's where it gets a little bit complex, and where I kind of have to balance what I go over here. I think to make it very practical, I'll show it from the perspective of when you're dealing with packed executables, in this case, UPX, what are you looking for? What's the pattern that you're looking for? So right now I've opened up Ghidra's graph view, and this will make it easier. This will allow us to visualize the flow of the program. So let's see, it would go through to there. We can click into functions, and there you go. So that's getting past the entry point to the program. And so here we can actually see a visualization of the program flow. And I'm not going to analyze each of these functions and routines. That's going to be a waste of my time, because I already know this is code associated, or this is logic associated with unpacking this software. So the way that packing works is that it takes the original executable, compresses it, encrypts it, whatever, and it stores that compressed or encrypted output in another executable, kind of like wrapping around it. And so when that other executable is launched, it has a little bit of code that that is invoked, that then is able to decompress or decrypt that inner compressed executable. So it kind of nests it inside of itself. That's how a lot of packers work. So what we're trying to do here is identify where is that inner executable actually stored. So because of the nature of packing, what will happen is that there will be points in the program execution where it seems like it just stops with, it doesn't loop back, it doesn't, these arrows don't flow anywhere else. And this is particularly for UPX. Maybe it's not too general for packing. I'll just say it's definitely for UPX. Seeing the a flow that ends in a dead end, it looks like, without any return, that's what we're looking for. And that's actually what we have right here. So notice that this this box right here doesn't go to anywhere else that this program can see. It has a jump operation, so that's a little bit into assembly, but you can just, the way you can understand that is that at this point, it's jumping to execution in another part of the program's code. And this is a memory region that it jumps to. But if I click on that and I try to go to it, it's going to say that either it doesn't exist or there's like nothing there. And sure enough, it is in bounds of this program, but there's just unknown bytes, or yeah, it's pretty much nothing that we care about. And this is the nature of packing, is that before it actually runs, these sections, which would have held the original executable, will just be these unknown areas. So this is the extent of what we can do right now in Ghidra. It does have a debugger, but I do prefer using x64 debug for this, because we have access to a plugin called Scylla, which we will need. So now that we have identified this jump. And what is the significance of this jump? This is actually when the packer runs, and it's a little bit of code that handles the decompression and decryption. It's called the stub. When it wants to actually transfer program execution back to the original executable, it needs to go to a memory location of the original executable after it has been unpacked. And that's actually what this is. This is called a tail jump. This is a large part of the way packing works, so that at this point of execution, the inner executable, the original executable, has already been decompressed, decrypted. And when this jump happens, it's actually going to the original entry point of that executable. And that matters to us because this will help us when we are going through the debugger and we're jumping between memory regions during runtime. We'll use this as our kind of our anchor, so we know where to look. And let's see. The green line that intersects the code block, I think it kind of goes behind it. I don't think it's necessarily part of it. That's flowing from here up, and I think this is an arrow back. Yeah. Yeah, I'm kind of comparing it to how I'd usually imagine that in IDA. IDA is another disassembler. Yeah, but without making any assumptions, I don't think it's tied to this sort of this last box here. Is that a jump in the stack frame? If so, could this mean that stack frame is no longer available, which is why there are question marks in Ghidra? It's that this wrong place, this location that it's jumping to, it's not until the program is actually executed and the packer restores that location with the original contents of the executable. Not until that happens will this actually will that where did that go? Here you go. Will these question marks go away? And we will actually see code there. We'll yeah. And actually, I think it's better I show that now. So we'll open this up in a debugger. Okay. So this originally already has a breakpoint, I believe, at the entry point. Or maybe not just yet. Let's actually just go on ahead. Is this already the entry point? There you go. So here we are at the entry point. And similar to how we were looking for the end of flow in Ghidra, that's also something that we're going to look for here in the debugger. So it's not executing right now, it's paused. But the most surefire way, at least most of the time, to identify the area of interest for UPX packed executables is looking for these patterns. And this is very similar to what you were seeing in Ghidra with those question marks. These are entire areas of the of memory that during the program's execution that pretty much don't hold any data yet. And they're it's not just looking for this pattern though. Remember, we actually already have something to work with. We have that that memory offset that we can look for, because that is where the tail jump goes to pass execution to the original executable. So that would be here. And is that correct? There's a jump to ending in 61 to C4. Is that what we saw in Ghidra? Let's go back to the graph view. And I might have actually, there you go. Scroll, 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 scroll. And I already see it in the bottom left, I think. Oh, no. Oh, yeah. So 12C4. Was that what this was going to? Let's make sure about this here. You can match the runtime and launch time with the network traffic packet capture timestamps. Yeah. So question back up, was the box that ending in A before C a stub or no? The stub, it's not necessarily just this area, but the way I would describe it is that after a lot of this this logic that's associated with the packer has executed, and I believe this should even have Win32 API functions that kind of give away how it does it, like virtual alloc memory operations. There you go, kernel 32. What is this? Virtual protect. Okay, so prior to that area, above the higher in earlier in the execution is where it's running these operations to restore that original code. So the stub actually takes place earlier than just what we're seeing here. This is just called the tail jump, where it's passing the execution back to the original code at this location. So now that we've actually identified the same area in memory, we're going to actually set a breakpoint. So what that means is that when we continue execution, it's going to pause here, and we'll be able to see the original executable unpacked. So if we go to this area right now, it's going to be nothing around here. And all right, let's see. If we just go and continue, it should stop at the breakpoint right there. So let us step over. Let's just let that go to that location. And here you go. We see that there's now actually code there. You can see that it's been restored. This is the actual unpacked executable. So what just happened there? Before, we were seeing nothing. It was essentially like in Ghidra, you were seeing those question marks that was at this region. And let me just I'll restart execution here to make that easier to catch for anyone who didn't. So we'll go back to the entry point. Scrolling a little bit down is where we can see the tail jump. We set a breakpoint here so that when it jumps to this area, which is currently nothing there, that when that jump happens, this particular region will have restored the unpacked executable that we want to see. All good. Yeah, I mean, yeah, good points about the correlation between network and process execution. Yeah, that's definitely a thing. All right, so yeah, when we actually follow through with this, so we continue on, so we allow the program to execute up until our breakpoint, which you can just call it like pausing the program. Now we're, instead of, I think we should actually already see, yeah, we can even hover over here, over this location to see if we were to click on it, what's there. And remember before, it had all of these operations, which are essentially no action. It's just no operations. Now it actually has the restored code there. And this is the power of being able to pause execution so that we can access memory as the program manipulates it during its runtime. So, and this is very much like when we're dealing with encrypted strings or shellcode that the program protects when it's not running, but then when it's running, a lot of malware will decrypt that, and then we'll be able to access it in the debugger. But it's not a sure thing though, because there are methods where you can even encrypt your shellcode during runtime, and it's especially when coupled with things like sleeping, where you have times where your malware has no activity. You don't want EDR scanning that executable in memory and then finding that there's some shellcode or evidence of strings that give away that it's malware. So it can actually have encryption during runtime. It's just more functionality the malware developer has to put in. But not everyone does that. All right. So let's go ahead and bring the execution over to here. So what this means is that this is the actual entry point of the original executable. So we're going to now dump this original executable now that it's unpacked from memory. And to do that, we're going to use Scylla. And we just need to make sure that this is looking at the right entry point. That is. There is a sequence to dumping it. At least for me, I search for the IAT, which is the import address table. Remember we talked about DLLs, that with Windows programs, or really with most, if not all programs, they import ready-made code from other libraries, from other files, so that that code doesn't have to be in the program itself. And in this case, a Windows program would import DLLs, which contain code libraries for functionality it needs. The imports for those DLLs, like the DLL names that are used, those are stored in the IAT, the import address table. And that's actually part of the portable executable format that's been documented in one of the data sections. And but that's not necessarily the source of truth, because it's part of attacker tradecraft. You can actually spoof the IAT, or you can hide imports from the table. It's this particular thing called resolving imports at runtime. You can pretty much bypass using the IAT and make it harder for static analysis for any scanners that were relying on looking at the IAT to see what sort of DLLs this program was importing. But in this case, looks like there is content in the IAT. It's just importing of kernel 32. And so now that looks good, let's go ahead and dump this. But the issue with this dump, though, is that the IAT will actually be offset from where it originally was in the program. And this is largely because of it being packed. It kind of shifted the key portions of the executable to different areas. So we kind of need to shift them back, or adjust the execution flow to now handle the new areas. Either way, I think that this is actually restoring the IAT sort of location. So in order to do that, we've already dumped it to this location. We're going to do a fixed dump and select the binary that we just dumped. So, okay, it looks like that was a success. So to show the difference here of what we have now versus what we're going to see that we just dumped, if we go back to Ghidra and we look at strings. Strings are still very important with malware analysis. Strings are looking for, not here, looking for human readable, pretty much sentences or words, like for example, virtual protect is a function that malware can use. That is a string that, when shown up, can tell an analyst that this malware is doing something with memory. It's changing permissions to memory regions. So we're going to look at the strings before when it was packed. So let's take a look at that defined strings. And sure enough, because of the packing, this is pretty sparse. Normally, string output would be, for a normal program, it would be quite a lot. Question, does that mean in Scylla 64 we patch the executable to our desired outcome? Yes. After dumping it, we need to fix the import address table because it's kind of been shifted, and that's what Scylla really abstracts away how that works, and it's maybe not necessarily something I can speak in detail about. Maybe I can update when I verify to make sure that my idea of it is correct later on. But in a way, yes, it's patching because it's modifying that dumped executable and shifting around content inside of it to make it work. So we just saw the packed string. So now let's actually open up in Ghidra the dumped executable. And for that, I'm just going to save this one first. And we're going to just drag and drop. I could have just done that. Okay. And also might as well throw this into dnspy and see how dnspy analyzes this. All right, so it's still seeing UPX, but not because it's still UPX packed. There are actually artifacts of the UPX packing that it's still the original executable, but I can actually show here that what would have been the text sections, the PE sections of the original executable, they still have, for example, UPX here. You won't see like the R source or text sections still. But that doesn't mean that you won't still be able to analyze this. It still has restored code. And if you recall, when we were looking at the packed executable in the hex editor, this was a lot more jumbled. So, okay, let's check out Ghidra, but at least dnspy is now seeing that this is just an unpacked executable, except for this heuristic that's probably just seeing those UPX artifacts still in there, and it's probably why it's still claiming that. So, okay, Ghidra, let's open this. All right, so this is analyzing. You can see in the bottom right that it's doing its thing, decompiling. Okay, that's hopefully not going to take too long. All right. Okay. It's interesting. It takes magnitudes longer on this VM than when I was testing on another similar type of binary in my analysis lab. All right, it's almost there. I'll field some questions in the meantime. Did I miss any? Okay, maybe not. All right, there we go. So we should already be at the entry. And indeed we are. And here you can see that 12C4 was the entry point that we were looking for, the one that the packer transferred execution to, that location. So would you be able to do a recap from the function graph onwards? As in use that as a way to explain, or just explain again how that happened. All right, so let's check this out. And already you can see that the decompilation is different from what it was before. And what was, I give this again. So this is C++. And that makes sense. And this is using the CRT, I believe. So I guess to boil it down, when we're looking through this code, this is a function here. This is a lot of, it's not actually part of the code that we care about. It's, remember I was talking about even before main, there's a kind of pre-entry point where things like the C runtime set things up for execution, and part of this code is that. But we're actually interested in this common main. And here is where we're seeing the decompiled form of this malware. So let us see. Probably be easier to view this like this. Okay, yeah. Explain the process from flow graph onto present when it's a good time for you. All right. Yeah, no worries. There'll be time to recap after. We're pretty close to the end here. So, all right. Just tracing execution down. Where was this? You can actually still highlight where things are. That's up there. Okay. So this part is going to be a little bit hand wavy. It's just in the interest of time. If you were to get through all of this, and then a lot of this you can determine as that initial setup for the runtime before actually getting to the real main. And you can actually see a lot of things like startup lock, narrow environment. These are kind of indicators that this part of the code is boilerplate that we don't necessarily care about. And then as you get to the end here, this is where we actually, particularly this spot, I believe, is, or actually here is where we'd go to. That is get module handle. That is not where I want to go. Let's see here. I'm entering a function now. And all right. So this looks promising. And this is something that when you're looking at malware, it will be a bit of an aha moment because it's so often used. We actually saw this at the very start of the class, XOR. And that's what's going on here. Remember the caret? So it's all jumbled now because of this decompilation output. And I mean, it's still readable. It's just with a lot of the particular syntax that Ghidra uses to label things. So it looks a little bit more chaotic. But we can see the same pattern of values getting XORed. So the way this is working, and let's recall what this program was even doing from the get-go. Let's open up PowerShell again. And it was asking for a password. So what this is actually these XORed strings are storage of, you would guess, critical or like sensitive data for this program. So it sounds a lot like the password or other things. So the way that you would actually look at this is that these are stored in data. It's not necessarily on the stack. So, and that is like on the stack in memory. So the way that you would get to it in Ghidra is actually by double clicking these portions with dat. And you'd be able to, on the left, then skip right to the bytes where that data is stored. And that's in a different location of the executable. And So let's just sample this. Let's see what this one is. So we're just going to go ahead and right click, copy special, and we want to get the byte string no spaces. And let's put that into CyberChef, because this is an XOR operation. So I can actually just click on that. So first, we're going to convert from hexadecimal, and then we're going to apply the XOR. But what is the key is the question. Do, while, remember, loop, when it comes to XOR operations, this is a loop just in the decompiled form. The way that you would read this is that do this thing within the curly brackets while this constraint, like it's kind of until this constraint has been met. So it's very similar to the loop that we saw at the very start. But the reason why I've honed in on this is because I see the XOR operation, but I also see this as 0xAB, and that's actually the key. This has drifted quite a bit actually from the source code, and it might be the way that the compiler moved everything around, or I'd have to actually look into that, because some of the ways that this changes is surprising. But either way, it's still what we want. These encrypted strings they matter to us. So looking at this looks like a key, AB in hex. So let's try that out. All right, so we're actually getting readable content. It's just kind of broken up. So let's hunt for more. So let's go to the very top. And let's see, some of these actually are, maybe that real one doesn't really matter. I'm interested in this guy, 7F90, all right. Oh, I could have actually just, it saves it in Ghidra, it saves your last operation. Let's get that. Did I not? There you go. Those are just null values, okay. Actually, you should have seen that coming, given where this is, but let's try. Let's try this one down here. Nothing in there. File name A. Could not get X. Okay. So I'm just going to continue down and see if we can get close to some of the original content that we were seeing. And just to cover all ground, if I were to search for this string, say password, because you can do this in Ghidra, if you already know that there's some string in the program that can tell you, kind of give you a hint of the point in execution where you want to analyze, what you can do is, if that string is actually not encrypted and it's available, searchable, you can go to define strings, open up this window, and you can go to the filter, and just probably better to just have one thing. And if it is encrypted, if it weren't, and if it were just a plain string, just in the decompilation output, it would show up as a row in here. But I'm sure if we look up something like virtual, yeah, so you would see strings like this. These are to do with memory operations, Windows API calls. So one thing to keep in mind, just to cover all grounds, there's always an easier way to do something. Goes triply for malware analysis. All right, let's check out this. Totally fine.exe. All right, that's pretty interesting. So let's look through a little bit more. Might have been one that I already got. Let's see. Did I just go over again where I was? I think I did. All right. Incorrect password, and then kind of cut off. So that is confirmation that we are looking in the right place. Incorrect password. Question, why are we not using the whole XOR key? That is the whole XOR key. So these operations, you can see these individual loops acting on this data. So here, I guess to best describe it, here is where it's preparing the data that is to be XORed, and this is the actual loop where that XOR operation happens, and that is the key. Very similar to what we were looking at with the other program. Is that still open? That is, yeah, very similar to this, except this time it's not cycling through the key; it's just using the single byte. All right, so in the interest of time, I'll already let's see, where was that? That was this guy. What is this? This, that. So this particular one is actually not using a separate data location. This is actually on the stack. And let's see here. Yeah, I already looked at that. Okay. So I can make it out just from, and this is like a, what is that? A null character that it's checking for. This looks a lot like the password, just a little bit out of order. Yeah, sure thing. Yeah, so in this case, this particular thing is stored on the stack, and that is interesting. Drop D, and then, okay. So this is in an EA, this is AB. All right. ROPEAB. Yeah, so in my head, all those together, that's drop bear, which is an Aussie joke. That's not how you spell echo. So that's pretty much from the stack we can see. And the reason why that looks like the password to me is because that is on the stack just there, right before we decrypted, where it said here, incorrect password. So at some point before this, probably there is a comparison. Here you go, right here. This is actually the comparison here. If the contents of this is not equal to the contents of this, then this happens inside this if condition. You can see the squiggly denotes what happens after the if. Like if this thing happens, then do this. So we already know that this was saying incorrect password. So that means that if these two values aren't equal, then it's incorrect. So the password is in either one of these, either in CVAR2 or CVAR1, and you just have to trace back to how these variables were populated. And looks like this one, CVAR2, is actually what the password, where the password was stored, and that's coming from this stack up here, stack strings, I should say. All right, so that's drop there. So if we try this, drop there. So making ground, password correct, but one more secret check failed. And so there is still more logic to go through, and I kind of spoiled it, I think, if I remember how this thing goes. It's been a bit. We actually decrypted a string that I think gave it away. But, and let me just orient myself again here. I did not copy that over properly. Interesting. Okay. I clicked on something that I never clicked on before in Ghidra. Okay, so that's where we were initially. There was a string down here that was like totally fine.exe. I think it was actually more towards the bottom. Probably this guy. Secret check fail. Okay, so we're getting closer. Let's check out this. And this is a very manual process. All checks. Okay. The proper way to go about this, especially if you're going to have like a ton of, oh yeah, thank you, totally fine.exe. That's what we saw. Yep. But in the cases where you're going to have a lot of encrypted strings, obviously you don't want to be going through them individually like this. It's just because I need to keep this in scope. The proper way to handle this is through scripting it. You can plug in scripts like Python and JavaScript to these tools like Ghidra. Ghidra has support for different languages. My choice is Python, and you could, yeah, you can totally script this, especially if they're using the same XOR key throughout all these operations. Then this entire thing can be scripted, and then you just make sure to target the right locations of where this data is stored, because remember, there's actually a dedicated storage area, excuse me, for these things. Yeah, so something to keep in mind, that this isn't necessarily the best example of how to handle this. It's just for the sake of keeping this this workshop in scope. Wow, copy really does not want to work here unless I did that wrong. Oh, it would help if I'm actually on the right one. All right. At this point, I think it's better to already start looking again at the code, and we already looked at this. All right. I don't know if we necessarily have time to look into that, but okay. Pretty much that totally fine.exe is something that you would quite often see with malware. It's one of many evasion techniques where it actually checks its own name. It's the name of its own executable. It verifies that it's what it expects before continuing execution. And this is especially something that happens in the middle point of an infection chain when you have multiple payloads. And so the parent process of this malware, for example, it can check the name of that parent process to make sure that whatever launched it in the infection chain is what it expects it to be, and not some something that's part of a security solution that's analyzing it. And it can even check its own name, as that's exactly what's going on here, and that's the reason for that totally fine.exe. So without just going into all these strings, pretty much we would rename this. And we should see different behavior now that we actually name it that totally fine instead of the original mangled name. All right, and we know that's a drop bear. And there we go. It actually spits out a flag. So the remainder of these strings were actually the rest of the flag, which is why one of them decrypted to like a hex output. All right. That was a bit of a marathon. I know I need to take a drink for a bit. Any questions? Actually, I know that there were some requests for recap, and I will go about that right now. I do actually want to try something, though, that I might have forgotten that is just better practice to do. Just bear with me on that. And I might as well clean up all this stuff. Okay. Where's the binary? Let's name that. We can just leave that. Come on. Pretty sure PE Studio had the ability to manipulate ASLR. Nope. Should be optional headers. Here. Address space layout randomization. Can I not change that? Read only. Yeah. Okay. Let's try CFF Explorer. So something I actually didn't mention is that when you're dealing with before you even analyze the malware, it's good practice to disable ASLR, and that's address space layout randomization. It's not specific to Windows. This is something that's been implemented for program security for a while, along with things like data execution prevention. These are all ways to mitigate, I should say, the effect of exploits that can redirect execution flow in the program for malicious means. And in particular, ASLR actually jumbles up the memory locations that the program uses. So, for example, what we'd see in one of our analysis tools like Ghidra would look very different once we actually disable ASLR in terms of those memory locations. It would shift over by some magnitude. So what I want to actually do is disable that because I wanted to see if it would have different locations. I should be able to do it through CFF Explorer, and it should not be read-only. Curious why that was the case with PE Studio. All right, so disable that it can move. That's pretty much ASLR disabled. Yes, I want to overwrite the original. All right, and let us try that again just to make sure. Okay. Pop that back into Ghidra. All right, and while that's going, I can go over again a recap. So what was the question again? Like what particular part of the flow graph should I go back over? I know that was actually quite a lot in a short amount of time. So definitely would want to clarify things there if needed. Flow graph until the present. Okay. All right. I wonder if I have an old Ghidra version on here, come to think of it. No worries. So let's go back to the control flow graph. That's actually, it's not control flow, but the visualization of the original packed binary. So what we were looking for was, and I should do it through here. And actually, before I do that, let me go ahead and disable ASLR for even the packed one. Which was this. Topic of ASLR functionality in the code again, please. Like what ASLR is for. ASLR is address space layout randomization. So that's like these memory offsets that you would see. Pretty much you can think of them like the locations of code in the program or like execution points. If whether ASLR is enabled or disabled, those would actually show up differently in analysis, because that's the randomization aspect of it. It will actually randomize where certain things are loaded in virtual memory. So where is it more of the raw? But either way, it makes it harder for exploits to work. For example, if they rely on certain offsets or certain logic to be at certain locations in the program, and this randomization makes it harder to pinpoint where things would be, and so that's the reason why that's in place. But it just gets in the way of analysis. We don't necessarily need it. It's not important for us to understand what this thing does. It's especially when you need to compare these offsets between, say, x64 debugger and Ghidra. You want those to be the same, so you should feed the same executable with ASLR disabled to both at the same time if you're using them to correlate. And that's actually a very effective workflow where you can look at the decompilation output and the debugger execution at the same time and use them to inform each other, because it's very easy to get lost, and having them both with their strengths and the different ways you can gain information available, especially synced to the same memory offsets, is a very good way to go about analysis. All right. And what was this one? Totally fine, which is the original packed executable. So let's bring up the graph. All right. So when we're looking at the graph, this is just based on the pattern with the UPX packed executables that there is eventually a portion in the flow when the execution doesn't come back to anywhere else in the graph. It's kind of just like it stops short. And in that case, this is this jump operation to this particular location, and which in this case is not a defined function because of the nature of how packing works. So that will be available after the packer has restored the original code. The easier way to look at this is when we were actually in x64 debug, because here it's a lot more obvious where that point of interest is. Okay. So let's go to the entry point, and we were scrolling a little bit down until we got to this area of like junk. This is called the tail jump. For UPX, this is a very common pattern, and it corresponds in this case, and this is actually, let me make sure of that, what I'm just about to say here. All right, this is ASLR disabling in place. So one thing I was concerned about before was that these addresses between Ghidra and between the debugger at first were not matching up. At least only the latter part of the address was matching up, and that's because the like down to the smallest bit of the location, the offset, it's still the same, but then overall it was shifted. So that's what ASLR does. The layout of these locations gets shifted around, which is why we were actually seeing before this had something like 14B E9 whatever 12C4, and the only thing that was similar was the 12C4 at the end, which correspond to what we're seeing in the graph here for 12C4. So they were very slightly different because I had forgotten to disable ASLR before loading the same binary into both x64 debug and Ghidra. So now that ASLR is out of the question, it doesn't add any more variation to these offsets. They should have the same reference, the same addresses that we're referencing here. So these are the same places. This jump operation to go to this location and execute whatever code is there is the exact same thing as we see in the Ghidra chart. Same thing as we're seeing when we're actually looking at the debugger here, where there is a JMP jump operation to this location. If we click there, currently there's absolutely nothing there. Again, because of how unpacking works. And this is exactly why when we look at the graph in Ghidra, it's like it leads to nowhere. This is that nowhere. But when we put a debugger down, sorry, a breakpoint down, and the way you do that again is that you set this red dot on the left. If I can, there you go. And this is where it matters. We're just going to put a breakpoint there. Going to run until that area. There you go. It stopped. And remember how I went into that and it was nothing there? Guess what? Peekaboo, there's actually code there. This is now the unpacked data that's been restored. So what we did with this, to recap further, is using Scylla, or Scylla, I'll say Scylla, we dumped the contents of this now unpacked executable. And previously, it had actually already given us the correct entry point. This particular location here has to be the original entry point of the executable, which is this, because this is the location that the packer sent, transferred execution to. This is the entry. This is the entry point of the unpacked executable. So we actually want this memory offset, and we can copy the address, this address, and we'll put it into Scylla, so we have the right one. And then it's again what we were doing. We were restoring the import address table. I kind of just quietly deleted this. It's just something that always happens. You know what? I haven't actually gotten a clear explanation of why that's done. I saw it once and I haven't questioned it, which is not good. I really should be questioning why we delete that or why that even comes up as an invalid import. I'm going to look into that because actually I really should know that. So let's go ahead and dump that, very much like what we were doing before. And then we fix the dump, which is restoring that shifted import address table. And that's where we were able to get the unpacked binary. And then we did our analysis. We were able to actually now with Ghidra look through the logic properly and determine. That's how we got to those XOR encrypted strings in that stack string, and where we were able to bypass this this password check logic, and even find out that it's checking its own file name before doing anything. Is it like some parts of the code execute in heap, some in stack frame, and some in code level? Not across all those things. It's just the location. So when an executable runs, I mean, it still has its sections of where certain things are meant to be. Data, code that executes. They all have to be mapped to a certain region of that executable in memory. So ASLR is just randomizing where those things are mapped to. So when you say heap and stack and code, I wouldn't say it's part of the stack. The stack is a different thing. That's more of during execution, having data available to that. Maybe that I'd have to check. I don't think so that would get shifted around. Maybe as a whole with everything else. But definitely like code regions and data would get shifted around because of the ASLR effect. All right. Well, that was quite a lot. So it's actually less than I wanted. It might be a next time that said what's the word for it? Tip of my tongue, tentatively. If I hadn't remembered that, that would have been on my mind for the rest of the day. So tentatively saying that this will be the soft finale for RE4. We've worked from high-level languages like Python and even scripting like PowerShell, gone sort of to the middle with bytecode languages like .NET, which is not necessarily, I mean, it is compiled. It's more like pseudo-compiled. And now what we've done is we've taken a look at C++ and C compiled executables, and not only that, we're able to defeat packing. And in this case, it was actually a packed executable that was mangled a little bit, so we couldn't even use the original packing tool to restore it, which is why we had to dump the contents of the unpacked data from memory and then work our analysis on that. So yeah, sure thing, Karina. Yeah, sorry about the tech issues. The only thing I could think about, trying so many things was like, do I really have to delay this stream? But I'm glad it actually came to be. I'll just chalk it up to gremlins in my computer because, again, it was just restart and then everything was shipshape. So not exactly sure what happened there. But yeah, thanks for coming in. Everyone who's asked really good questions. I had a lot of fun. It was great to discuss these things. I love sharing this skill set. I'd say before I sign off on here, I do want to mention that these workshops have been really just hands-on, where I go through the process and then you ask me questions, I clarify things. But there is actually still the course content, which I'm going to go back through here in SOC 105, and these will act as augments to what's up here with the recorded stream. So if you want to go back and rewatch this, the recorded streams are posted here and on YouTube, and I think maybe on Twitch. But the content down here that will be kind of backfilled will be supporting what was in those streams, but that will come a bit later. Have to pivot focus for a little bit. So will the recording be up soon? I think that is a question for Anthony. He is the guru with cutting up, editing the recordings, and he even has it down pat, the process. He has that thing down to a T. So yeah, that is very much Anthony and his skill. Yeah, sure thing, Rizmedo. I'm very glad. Great questions. Yeah. Yeah, and then also, so that was that about this content coming in, along with some challenges that reflect some of the obstacles that were demonstrated in these streams. But I also want to, and I'll use the VM for this, share some what I think to be really good resources that you could look into just on YouTube. So let's check that out. If you would like to continue down this and you'd like to get into deeper waters, I highly recommend the Cyber Yeti, who used to work for Mandiant and was or is maybe, not sure where he is now, but he was part of the Flare team, which has made leaps and bounds in the world of malware analysis, malware research, and reverse engineering. So I will put that channel link there. I also recommend, I think the name is the Cyber Raiju. This might be a little bit harder to track down. How did that turn into, what is that, SU? Or, no, experimental aircraft. Interesting. Interesting that turned into that. Oh, Raiju Cobra. Duh. That looks a lot like the F-35, probably for good reason. So anyway, Jai Minton, I think, is the other way that he goes. There you go. And this is, to me, really fun. All of these videos are a joy to watch. They're all about malware analysis, like really interesting malware. Think about steganography, hiding payloads in audio files, for example. All of that in here. So Jai Minton. I would also say, last one, malware analysis for hedgehogs. Down here. This one, not a bot. This channel I quite like. And all right, so there's that. And then these, okay, promised. Last one. There's also John Hammond, but I think I don't even need to share the link to that. Everyone knows him. He has the whole series of malware analysis and script analysis. But the last one, very, very last I want to share is OA Labs. This is actually more on the advanced side, but they have excellent content. So yeah, I hope that for anyone who's interested in continuing with this, and video content is the way to go. Those are my recommendations, and certainly have helped me skill up quite a bit. Nice, yeah. Thank you, Cyberkata. Or I might as well just say Doug. Thank you, Doug. Yeah, RE class, Karina. It has been thought about. It's just that there's already so much out there. Like on YouTube, for example, what was just shared, but even on GitHub, there are entire like hours upon hours worth of content with courses surrounding reverse engineering. And it's not just malware, it's embedded devices, all types of hardware, network analysis as well. Reverse engineering has a part to play in that. So yeah, I mean, it would be nice to make course content around it, but it's hard to beat what's already out there and even free. So that's kind of my thought process. All right. Well, we're about over the hour. That was a lot of fun. I had a blast ripping through that malware with everyone. I hope that was really useful and people learned a thing or two. And oh yeah, I guess so, Karina. We could definitely lean in more to the beginner's approach. That is true. That's actually not something that's maybe that gap has not been bridged enough yet. Yeah. All right. Yeah, sure thing. All right. Thank you, everyone. Have a great rest of your weekend. Is it the weekend? Nice. It is the weekend. Have a great rest of your weekend, and catch you again. We'll be doing more of this in the future. All right. Thanks, everyone. See you.